be talking about embeddings. So the previous two lectures, we looked at various forms of dimensional reduction, clustering, lane factor models, and basically learning some sort of low-dimensional representation of the data that somehow summarizes the data in a useful way. Summaries include things like, well, we minimize the residual squared error of some notion of a reconstruction, right? That's basically what all of the last two lectures we're talking about in terms of loss functions, with the exception of things like maybe agglomerate clustering, right? And so in this lecture, we'll look at a different way, although you'll see by the end of this lecture, hopefully, how they're all closely related to each other. But at least for now, a seemingly different way of learning a low-dimensional representation. And this will be this class of representations are known as embeddings, right? And in some ways, you can think of embeddings as a generalization of lane factor models, right? You can think of lane factor models as a special case. And so we'll start with a warm-up on locally linear embeddings. This is one of the first embedding approaches that was, picked up a lot of popularity in the machine learning community. And then we'll look at two more, I guess, contemporary versions of embeddings, specifically in sequence embeddings, including playlist embeddings and word embeddings. And we'll look specifically, in the last case, at a method called word2vec, which is on your homework. Okay, embeddings. So the goal is to learn some representation U, and I use this matrix U to denote the same semantics as the U in lane factor modeling, right? And so each column of U, a little u, represents a representation, I guess in this case, of a data point. So not exactly the same semantics. And so semantics are encoded via some distance function, right? And so, or rather, they're encoded by two notions of similarity. One is just distance, right? So if there's some notion of distance, in this case, a square distance in the Euclidean space that the representation lives in, then if the distance is smaller, then they're more similar. We could also use similarity via the dot product or cosine similarity, right? And so both of these are valid depending on the application and which one makes more sense. And I'll just note that in the latter case, this is going to be a generalization of lane factor models. Okay. Excuse me. Any questions on this before I dive into the first example? Okay. Okay, so the warm-up is on locally linear embeddings. So this was proposed quite a number of years ago. I want to say it's about 15 to 16 years ago. So some of you guys might have been in diapers back then. So locally linear embeddings. So given a data set of, in this case, just only the features, right? And no labels, right? So this is an unsupervised learning problem. We want to learn a U such that local linearity is preserved, right? So this U should have much lower dimensionality than any X. So if X lives in high dimensional feature space, you want U to live in a much lower dimensional feature space. But it preserves this property of local linearity, right? That's the idea. And this, you can think of this also as a version of what's called manifold learning. A lot of people refer to this type of learning task in the machine learning community also as manifold learning. Okay, so here's an example. In this very simple example, X lives in a three-dimensional space and U's live in a two-dimensional space, just for illustration purposes. And so this is the generating distribution right here, right? This is a supervised, or excuse me, an unsupervised training set sampled IID from the generating distribution. So those are the X's, and the color coding is simply for illustrative purposes. Okay, they're not actually part of the data. And the goal then is to learn for every point here, a point here, right? And so associate a U with every X, where this U is two-dimensional instead of three, so it's lower dimensional than X. And you preserve the local properties, right? So here, local linearity is preserved. And we'll formalize what local linearity means in a few slides. But that's sort of the basic idea, right? So if this is so analogously, a different way of saying this is, if this is a two-dimensional manifold living in a three-dimensional space, we want to actually learn a parameterization of this two-dimensional manifold. That is, in some ways, good, right? Any questions on Okay, so the approach, the property we want to preserve is some notion of local, some local behavior property, like the local linearity properties are preserved. And so we're going to use, the basic idea is we're going to define a relationship between each point and its neighbors, and then find a lower dimensional representation of that point that preserves that relationship. So this is a two-step approach. Okay, so the first thing we'll do is create a neighborhood, define a neighborhood for every data point, x sub I, right? And it's simply the capital B nearest neighbors, right? As defined in the original representation. The assumption is that in this neighborhood, the points are approximately linear, which means that they all live approximately on a plane, right? A hyperplane in this high-dimensional space. Therefore, each data point can be written as some convex combination of the data points in its neighborhood, if things do lie perfectly in a plane. They don't, but we'll relax this into an approximate convex combination, but that's sort of the basic idea. Right. So here's just a very simple example, right? So if all the data points lived in a one-dimensional, I guess this is two-dimensional, right? So you have a one-dimensional manifold living in a two-dimensional space, right? Then this data point, suppose we just look at two neighbors. In general, it's some number b, here b equals 2. Then you can approximately represent this data point as a combination, as a linear combination of its two neighbors, right? Of course, this isn't perfectly linear, but the reconstruction error of this data point as a combination of its two neighbors is going to be fairly small, right? That's the basic idea. And so the idea then would be to learn these W's, right? Learn these W's, right? So if every data point can be written as a convex combination, in this case, of its neighbors, it goes from this W matrix of coefficients subject to complexity constraints, right? Yes?
Is the constraint on the size of the B? The size of how many neighbors?
It's a hyperparameter in this particular algorithm. So you set it beforehand. And I'll show you some examples of different choices of B at the end in experimental results. Certainly, if things were perfectly linear, in this case, right, then B equals 2 suffices. You choose larger B to be robust to imperfections in the model, to model mismatch with the actual data and noise, and so on and so forth. Okay, so this is the learning objective for step 1, which is to learn the local structure around every data point, right? So that more or less, under this local linearity assumption, learning the local structure or the local relationship of every data point with its neighbors corresponds to learning this W coefficient matrix that minimizes the reconstruction error, right? So this is the reconstruction of this data point as a combination of its neighbors. And the reconstruction error is this loss function. I want to find a W that minimizes this loss function, right? We can do a bunch of standard algebraic manipulations. I won't go through the details, but at the end of the day, you could write it out. You could write it out in this form, right? Where C is this matrix. Right. So since the x's are fixed, right, they're pre-collected training data. We can pre-compute this C matrix, and then the goal is to learn a W that minimizes this objective, and they're mathematically equivalent. Yes.
What is the subscript star notation?
It denotes. Yeah, I sort of just borrowed this from that paper. It denotes a row, wait, a column. Yeah. Star just means all the entries. Yeah. Okay, so if we were to solve this, right? So if we were to solve this and get this W matrix, right? Then we've learned a set of coefficients such that every x of I is approximated as a convex combination of its neighbors. Right? So that's the idea behind solving this learning objective, right? Under the local linearity assumption. Okay, so to solve it, let's take a look at revisit Lagrange multipliers, right? So this is a simplified version of the problem, but it's illustrative. You know, if we're here, we just take a direct in the unconstrained version. So this is constrained, right? In the unconstrained version, this is, by the way, this is a quadratic loss function. In the unconstrained version of this problem, where this constraint doesn't exist, we just step in the direction of the minimum. But we have this constraint, right? And so it's a box constraint. So you know, if you're living on this part of the data point, you're in the model space, and this is the gradient, you project down to be on the boundary of the model class until you reach that corner, in which case the projection leads you back to the same point in the corner. And now you've found an optimal solution to this constraint optimization problem. Just the recap of Lagrange multipliers should be reviewed at this point. Right. We could similarly write out the Lagrangian of this objective. So you know, put the constraints here. Compute the gradient with respect to a row, or column, excuse me, of the matrix. And setting it equal to 0, you get this solution, right? So setting it equal to 0, you get that you know, it should be proportional. The solution should be proportional to the inverse of that matrix. And I guess it's not so important to follow every step of the derivation in detail. It's fairly standard manipulations of multivariable calculus and linear algebra. The point is to sort of just to illustrate that it's actually just a few number of steps, and you could derive this as the solution of that objective. And these are the types of algebraic and multivariable calculus manipulations that go on in all sorts of machine learning formulations. Okay, so that's the solution. What are some nice properties of this, of having this type of solution? Well, it's rotation invariant. So if we have a rotation matrix A, right? You know, it will if this property is true, or I guess I put squiggles here. So if this property is approximately true, if I rotate everything, it's still going to be approximately true. It is invariant to scaling. So if this property is approximately true, that approximation will still be true if I scale everything up. The approximation error will also go up by an appropriate scale, but relatively speaking, everything's preserved. And it's also translation invariant. So this property really only just looks at the local neighborhood, right? Any questions on that? Yes?
So if we wish to reduce the dimensionality of the intersect, are we required to choose at least the dimensionality or the cardinality of B is smaller than the dimension of X?
Ah, interesting. No, you should choose B to have higher dimensionality than dimensionality max 2. Otherwise, you get right. If you live in a d-dimensional space, okay. Actually, let me think about this for a second. So B should be, so if you want to learn like a k-dimensional embedding of a d-dimensional space, like k-dimensional manifold, where k is less than d, capital B needs to be at least as large as k. Whether or not it needs to be larger than d, the dimension of the raw dimension, don't think there's a guiding principle on that necessarily. Yes?
I guess as a follow-up, what sets the dimension k?
That's a hyperparameter. It's like it's same as the number of link factors, same as the number of clusters. Yeah. All right, so that's the story so far. We want to want to learn the local relationships of every data point relative to its neighbors, and this is the solution. So now in the original representation, we've established a locally linear relationship between every point and its neighbors, right? So now we want to learn this U, right? So the goal is to actually learn a low-dimensional representation that preserves or approximately preserves some local linear property. That's the purpose of this entire exercise, right? So we've learned. So what we've just done is we've learned a local linear property from the data. We've extracted from the data. Now we want to learn a U that preserves that local linear property, right? So now we have this W. We have this W, and the W is fixed. We've learned it already. And now we want to learn a U. We're going to learn a representation for every data point such that it also preserves approximately this same relationship. Right, so if you have a red data point here and it can be represented as a function of its neighbors by that W matrix, we want to learn a U such that that red point is also the same function of its neighbors in this new representation. That's lower dimension. Okay. So, we have another minimization problem, but now we're going to hold the W fixed when we learn a U, right? Before we held the X's fixed, these were X's, and we learned the W, now we hold the W fixed and learn the U's. And they're going to be lower dimensional than the X's. We put a few constraints on the U, because U is actually under constraint, right? Because it's translation invariant. You could actually shift all the data points anywhere, and it wouldn't change the learning objective. And so we just center the data, right? So we put a few constraints. This is basically to make it control for the rotation and scale. Okay, so we can rewrite this objective. Again, this is just fairly standard linear algebra manipulations. We could rewrite the linear objective in the following form. Like this. So the trace of U transposed, where M is this matrix with the following definition. And now we can think about this learning objective, right? And suppose we only wanted to learn a one-dimensional embedding, right? So k equals 1. So then we minimize a vector, a single vector U, and the trace, equals this definition, right? And that is equivalent to maximizing the trace of this guy, where M plus is the pseudo-inverse of M, right? And by a very standard theorem, this is solved by U being the principal eigenvector of M pseudo-inverse. And recall M is this matrix here. For those of you who are who know things about concepts like the graph Laplacian, this is a very related concept. Just to recall principal component analysis, right? So if you have a matrix M and we decompose it here, I'm using V's instead of U's. We can decompose into this matrix where the V's are orthogonal matrices, and this lambda is a diagonal matrix with zeros on the off diagonals and decreasing values of lambda on the diagonal. Some of the lambdas may be 0. Right. Then the pseudo inverse of M is simply the same. Use the same V's, but you simply invert the lambdas, and for the ones that are 0, you just keep them 0. That's the definition of pseudo inverse. And what you get if you multiply a matrix by a pseudo inverse is you get basically a partial identity matrix. Up to the rank of the original matrix. Right, so for k equals 1, we get this solution. And it turns out that for general k, right, it's just the top k principal eigenvectors of M pseudo inverse, or the bottom k non-trivial eigenvectors of M. Or non-trivial means the ones that are non-zero. Right, so that the last couple of slides, I guess mathematically it was a bit dense, and typically in these, but to sort of derive the full solution, right? With this exercise, we derive the full solution, but sort of it doesn't. The main thing to take away from this is sort of what the high-level concepts that govern why we chose to use this learning objective, and what property we're trying to preserve, and why we think that's interesting. So just to recap this approach, so the first thing we do is generate neighbors for every data point. We compute a local linear approximation of every data point as a function of its neighbors, subject to convex constraints. And then, once we've learned this local linear relationship of every data point with respect to its neighbors, we learn a lower dimensional embedding that preserves this relationship as well as possible. And this embedding is learned for every data point simultaneously. Any questions on this whole procedure? Okay, so let's look at some visualizations from this from the authors who wrote the first paper on this. So here is the true distribution for d equals 3. This is the unsupervised training data sampled IID from this distribution. Again, the color codes are simply for us, for our reference. And we're going to learn a two-dimensional embedding, right, that preserves the local linear properties. And so then there's a choice of, well, what is B, right? How many neighbors should I use to define the local linear embedding? Here's what it looks like for B equals 3. Not the best. B equals 6. Kind of interesting. B equals 9. And B equals 12. So at B equals 9, it's sort of converged, right? And at B equals 12, more or less the same solution. And some of this artifact, you can interpret this artifact, right, as these parts correspond to the outside of the loop, right, of the roll, and these points correspond to the inside of the roll, right. And so there's, there's going to be a difference in curvature of this manifold between the outside and the inside, right? And our locally linear approximation doesn't actually take that into account, right? It more or less assumes, because it assumes the B, the capital B is uniform, right? Across everywhere in the data set. Whereas, if the curvature was higher, you would actually want B to be smaller, or you want things that are closer together. Because the local linear property becomes a very bad assumption as you get further and further away very quickly if you have high curvature in that part of the manifold. Yes?
For V equals 3, are all the data points still blocked? They're just all in the lower right-hand corner for the approximation? Or is there something like
Yeah, it's an almost degenerate thing. Yeah. In fact, I believe what happened here is they actually learned to almost disconnect, two disconnected components.
So there's the so that green is that green dot actually almost all the data from
Yeah,
the
absolutely, yeah.
let's see.
Yeah, you can imagine, right? If B is too small, you define this neighborhood, it's possible that you can disconnect the components. Yes?
But for this data set, it's originally in 3 dimensions.
That's right. We just reduced it to just for illustrative purposes.
Right, and then if you choose B to be 3, and if the 3 instead of being represented by the 3 points are actually lying inside that common set, enclosed by that 3 point, I don't think we should be able to get the original data set.
Ideally, should get the original data set. So, okay, so one thing I didn't show is so this is, okay, so here I'm only showing U's, right? I'm not actually showing the reconstruction of the W. So potentially what you could do, and this is a good idea, maybe I should show this for the future reference, is that after this step, right, you could try to reconstruct each x of I using a combination of its neighbors and look at how good that reconstruction is. So we didn't actually show that, but that's something that you could check. Yes?
So here K is the dimension of the manifold, and B is how many number of points you use to approximate that point, right?
That's right.
So, is there a way to vary B across the data set? You can measure like how
Yeah, I think it's a natural thing to consider. They didn't do it in this first paper. There may have been follow-up work that looked at that. Yeah.
What's the intuition behind like the funnel shape and the plots they check?
So my intuition is that these points, these points correspond to the inside of the roll. These points correspond to the outside of the roll, and the curvature of this manifold, right, is different, or not even just curvature, the distance, right? Things are just stretched more on the outside of the manifold, and things are curved more and closer together on the inside of the manifold.
Why B equals 9 and B equals 12? I think that's what it is.
Well, it's the thing is, I mean, you get equivalent solutions, right? If I reflect this, it doesn't change the loss function. So there's a symmetry in this learning problem. So these are identical solutions.
That shouldn't correspond to any collisions.
I'm sorry?
If that's symmetric, then it shouldn't correspond to any geometric invariance.
If it's symmetric, it shouldn't correspond to any geometric invariance. If it's symmetric, I'm not sure I understand the question, the point.
If the red part corresponds to where the curvature is larger, or curvature is small, then in B equals 12, the red part should still be.
Yeah, it is. It's right here.
I see.
Yeah, it's right here. It just flipped. Yeah, because we're yeah.
So what is the result if B is really large?
I don't know. I suspect if B is really okay. If B gets too large, then well. I would not be surprised if you get more or less the same answer. Okay, so that was the warm-up. Now let's move on to more contemporary embeddings. So we're going to look at two in the context of probabilistic sequence embeddings. The first example of a sequence embedding is embedding a playlist of songs. That's sort of the motivating application for this particular embedding approach. And so the idea is that if you go to any of your favorite online radios these days, you have just an enormous number of user-generated playlists, right? And you could treat this as training data, right? So we have all these data in the form of sequences of songs, playlists. Can we learn a representation of songs, right, that can model these sequences? In this case, we'll do it probabilistically, right? The second example will be a word embedding. So people write natural text all the time, right? For example, news, blogs, etc. And can we learn a representation of words, an embedding over words, such that we can reconstruct a probabilistic model, encode a good probabilistic model of these word sequences, also known as sentences. So here's sort of the basic setup, right? We have a ground set, so the notation is a little bit different, so bear with me. We have a ground set, so you can think of these as each one being a unique song or a unique word. And then we have playlists, right, or sequences, right? So these are sequences over the ground items, right? You can think of these as playlists, documents, or sentences, right? And the goal and the sequence is defined as the following, where each of these references a single item in the ground set, right? And the goal then is to learn ultimately, and I'll reiterate this later, the goal then is to learn a model based on a low-dimensional representation that can encode a probabilistic model of sequences, right? So given that we're currently playing this song, learn the probability distribution of what song will be played next over all the playlists that I've looked at. Okay, so, let's say that there are, let's say 100 songs or 1,000 songs or 1,000,000 songs, right? It's discrete, it's finite. This is just a lookup table, right? An item by item lookup table, right? Something like this, right? So is the probability of going to song S sub I, S given S prime, right? So every row is so every column sums to 1. Can anyone tell me we could estimate this table from data. Can anyone tell me what's the problem with this approach? Yeah. Yes, it grows quadratically with the number of items in the data set. And you're going to also deal with a sparse data issue, right? If you don't see enough transitions from one song to another one, you'll estimate the probability is very low, even if the songs are actually pretty related, right? Just because you haven't seen it in a playlist doesn't mean that you can't imagine it being happening as a natural thing, right? If you knew something about these songs. Okay. So so this is the outline of the remainder of the lecture. We're going to look at playlist embeddings, which is based on distances, and we're going to look at word embeddings, which is based on inner products. Right. So I talked about those two differences in the beginning, and then we'll do a little bit of conceptual comparing and contrasting the two approaches, just to reiterate the word to Quebec is a homework question. Okay. So let's talk about Markov embeddings based on distances. So let U sub S be the entry point of a song, right? So this is the embedding. So U sub S is let's say, k-dimensional vector that corresponds to the entry point of a song, right? And let V sub S be a k-dimensional vector that corresponds to the exit point of that song, right? And then we can model the probability of transitioning from song S prime to S. So if we have a playlist, overall common playlist, we're currently playing song S prime. What is the probability that song S will be the next song in any given playlist that contains song S prime? Right. And we'll write that to be proportional to the negative exponentiated distance between U sub S and V sub S prime. We're leaving song S prime, we're going to enter song S. And then we can simply write out the probability by normalizing, excuse me. And here we sum over all possible songs, right, that we could transition to from song S prime. So, you know, we call logistic regression log linear. We could think of this as sort of log radial, right? And you'll see what that means. You'll see the intuition behind that in the next slide. But any questions on this so far? Yes?
What exactly is an entry point and exit point? Can you explain that again?
Yeah, so when you go from, so you have a playlist of songs, right? And you've just played song S prime. And then you want to model the probability that the next song after S prime is song S. So we will model. So then we learn two embedding representation. We learn two representations for every song in this embedding. The transition to that song and the transition from that song. And that's what you would VR. Yes.
You model the value of S as discrete points in a sequence, or is it some continuum? There's so much time between it, or is it like there's 4 songs between the start and the end of this one? How do you model?
The model only looks at neighbors, like immediate adjacent songs.
It's only adjacent?
We could do more complicated, but this particular version of the model, we just look at immediate adjacent neighbors. Yes?
Just out of curiosity, how well does the model do with missing data problems?
That's a great question, and we will get to it after we go through the derivation of this, and then I'll talk about missing data. Yeah. Okay. So here's what I mean when I call this a log radial function, right? Suppose we're exiting song S prime, so we're in this point in the embedding. So this is a 2-dimensional embedding for illustration purposes, right? And here are 2 entry points for song S and S double prime, right? You know, these circles represent level sets in the distance function, right? So all songs that happen to be on this circle are equidistant from V sub S prime, right? And all U sub S's on this circle are equidistant from V sub S prime, right? And so any song that sits on the circle, you know, basically has the same probability to be transitioned to, right? And so what are the number of parameters here? Well, if everything lives in a k-dimensional space, if these embeddings live in a k-dimensional space, then there's 2 times k parameters per song, which means the number of parameters total is 2 times the number of songs times k, which is much, much smaller typically than the number of songs squared. Right, if there's 10 million songs and k was 25, you're talking about several orders of magnitude difference in the number of parameters to estimate. Right, so let's come back. So why are we doing this? What are the goals of sequence modeling this way, right? Well, first of all, this is the data that we have. We have sequences over ground sets, right? We want to learn a representation over the ground items, in this case songs. We'll look at words next. We're going to learn a low-dimensional representation embedding over these ground items. The only thing that we have, or the thing that we're focusing on in learning this representation, are these sequences that people have generated using these ground items. And so how do we use these sequences to help us learn embedding? Well, you can think of these probabilistic transitions, right, as a form of learning some kind of reconstruction over these sequences. But we're actually learning the embeddings of the ground items to reconstruct these sequences. So there's a one step of indirection there compared to like latent factor models where we're actually trying to reconstruct the original items, right? You project onto some low-dimensional representation, then you back project. But here the thing that we're trying to reconstruct are the lists. So it's a little bit more complicated, but the same intuition holds. There's a reconstruction error, and then there's an embedding over the items that we're going to learn that will minimize the reconstruction error. And so because we take this probabilistic interpretation, the reconstruction error will be negative, it will be log loss, but first let me just write out the original learning problem. So we have our data set of our list of ground items. So in this case, our songs. We have a training set of playlists, and this is the playlist definition, right? So each of these entries corresponds to indexes one of these ground items. And then we want to learn a U and a V that maximizes the probability of the playlists, right, that we observe. And under standard independence assumptions in terms of sampling from some original distribution, these factorize multiplicatively, right? And we also make an independence assumption that these transitions, these adjacent transitions, are also factorized independently. So this also factorizes. So this is the learning objective. We want to find a U and a V that maximizes this probability. And what we're going to do is we are going to take the negative log of that, and so it reduces to this form, right? And this looks a lot like what you saw in the second week of class when you looked at logistic regression, right? Basically the same kind of derivation. Just that the form of P is no longer a linear function, it's something else. So we solve this using gradient descent. So we initialize U and V randomly, and then we compute the gradients on U and V with respect to this loss function. Similar in the ways that you've been doing it so far. One thing that's kind of tricky is that this normalization constant is expensive to compute, right? It requires summing over all possible songs in the data set to compute this normalization constant. So for logistic regression, it's binary, so you only have to sum over two possibilities. Here you have to sum over, if there's a million songs in the data set, a million possibilities just to compute one gradient of one data point. So there are various ways you could approximate this denominator, and I won't go over the details, but because that's sort of a low-level implementation detail, it doesn't really speak to the high-level sort of intuition. Any questions on this? Okay. Right. So what this allows us to do is, if we discover that through, if we discover that two songs have similar embeddings, right? They can have similar embeddings even if they rarely interact with each other, right? Because let's say one song often transitions to this song, transitions to this song, and then another song has a completely different transition, but these other songs are related to each other, right? Then we can actually learn to infer using values in this particular form that two songs are related to each other. Basically in the same kind of intuition as collaborative filtering. We could also look at simpler versions. So what I just presented was the dual point model. We could also just consider a single point model, just for simplicity. We learn only a single embedding over the songs of two, in which case, the distance function is going to use the same embedding point no matter if you're exiting or entering a song. We could visualize the embeddings. That's one of the nice things about embeddings, is that you can visualize them, or at least a projection of them, right? And so here's a visualization of the single point model, because they're easier to visualize. And you could see that, country songs are sort of over here. I don't even know what category Lady Gaga belongs to, but she's over here, and so on and so forth. And this is inferred completely from just the playlists, right? Just looking at the playlists that people create, we can learn a low-dimensional embedding over songs that have these semantics in terms of their distances, right? So recall that the reconstruction of the playlist it depends on the distances between two songs in this embedding space. So therefore, the closer they are to each other, the more similar they are in terms of the kind of playlists they fall into. Yes?
So the graph is the probabilities, or what does it show?
The U's. A two-dimensional projection of the U's. Yes?
Is there a way to like stop this playlist from going into loops?
Yeah, you can model start and stop states. Wait, when you say loops,
Loops as
sorry.
in like, you know, one song transitioning into song 2 and then song 2 transitioning back into song 1.
I mean, the problem, because of independence, the probability of that happening over and over again is geometrically small. Or it decays geometrically, is more precisely. Yeah. So we could, we could sample new playlists, right? So if you're currently at, this song, P super J, you can just you can compute these probabilities and then sample the next song according to these probabilities. It's pretty simple. So this is how you would use this model to actually do the reconstruction of the playlists, right? Okay, so what about brand new songs, right? What if we have a brand new song to the data set and we have very little information about the song, and it's appeared in very few playlists, right? So, under the model that we just described, the only thing we can do is we could set the U's and V's to be 0, because we don't have anything else, or some random initialization. And both are pretty terrible. This is known as the cold start problem, by the way, in collaborative filtering and in recommender systems in general. So in the movie item data set for the Netflix problem, if you have a brand new movie that no one's ever rated before, you have the exact same problem. Right. And so one approach that the authors of this paper took is they decided to learn a joint embedding over both songs and tags. So when a song gets added to the data set, typically associated with it a number of tags: country, heavy metal, etc. Right? And we could treat these, as attributes or features of these songs, right? And so one question then is, okay, how do we leverage these tags to generate reasonable embedding of new songs? So the goal then is to learn an embedding over the tags as well. And so here's the more expanded data set. So you have the ground items, which are songs, playlists, user-generated. Each playlist is a sequence of entries that indexes back to the ground items. And every ground item, every song, has a list of tags associated with that song. So T is a set of tags associated with each song. Right? And so the learning objective is to maximize the probability of tags and playlists. So this part is the same as before, right? Just over playlists. The song embedding, right, is we want it to be approximately equal to the average of the tag embeddings, right? This is the extra term that's added to the learning objective. Where A is the tag embedding. So we're going to learn an embedding per tag, and U is the song embedding. And we want the song embedding to be close to its tags. That's it. And you just solve the whole thing using gradient descent. Stochastic gradient descent. And so here's a visualization in 2D. Again, this is a 2D projection of an embedding that was learned. And so the country tag is over here, easily listening tag is over here, etc. And so now, if a brand new song, yeah.
But what are the axes on this example?
There are no semantics to the axes.
There, okay.
Because everything is distance based, there are no semantics to the axes. So now if you have a brand new song, right, that was just added to the playlist, added to the data set, and no user has created a playlist around the song yet, if you assume that the song has been tagged, you can initialize the embedding for that song as the average of the embeddings of the tags for that song. And this turns out to be fairly useful, at least much more useful than having nothing for that new song. And this initialization of this new song is implied by maximizing this objective. In this objective, this part doesn't exist because for the song doesn't appear in any playlists, and this part is maximized by choosing the embedding of that song as the average of the embeddings of the tags. Okay, so in the remaining part of the lecture, we're going to quickly cover word embeddings. It's going to use a lot of the similar concepts as what we've talked about already, but this is probably the most popular common use of embeddings these days, I would say, which is learning embedding over words, right? So given a large corpus, let's say Wikipedia, Google News, whatever, learn an embedding over words to model sequences of words, also known as sentences. Right? So previously we looked at capturing semantics of similarity using distances in this embedding space, which is what the song embeddings used. Now we're going to look at using inner product semantics to capture similarity. Right? This is basically a version of a lane factor model that we've seen last week. So, okay, let's talk about these embeddings, right? So what does it mean to have this as our probabilistic model, to model sequences over the ground sets, right? So, this was our V sub s prime. We're leaving this item, so we're leaving this word and going to another word. Then, basically, any other vector u that projects onto this green arrow by the same magnitude, right, forms a level set in the transition probabilities. That's the semantics. So the two blue arrows have the same probability. The two items corresponding to the blue arrows have the same probability to be transitioned to, and the two items corresponding to the red arrows have the same probability of being transitioned to. And otherwise it looks pretty much the same, right? As before, at least under this version of the learning objective, right? If we use the same adjacent neighbor transition probabilities, the definition of them is just this instead of based on distances. Everything else looks the same. We just train using gradient descent. Okay, but Word2Vec, that's so popular right now, doesn't use adjacent neighbors, or at least immediate adjacent neighbors. It actually uses a window of neighbors. Right? So it actually looks at a window of neighbors, including neighbors in the previous past. Right? This is also known as the skipgram model. So you can skip up to capital C, steps into the future or into the past. So why might we want to do this compared to just adjacent neighbors? Any ideas? Why might the people who came up with this model have been motivated to use this instead? Yes?
Negations might be separated by words by things like adjectives or adverbs.
That's right. So if you only model adjacent words, immediately adjacent words, the model can be too brittle. That's right. What we actually care about are semantics. Like if this word is associated with this other word, then they should be close to each other. And close doesn't necessarily have to mean immediate neighbors in a sequence. Right. So here, the word dog. I just made up 3 sentences, right? But here we can see that the word dog and the word fence have some mild relationship to each other, right? They have some mild relationship to each other, and that would not be captured. That would be really hard to capture directly in an immediate neighbors, adjacent neighbors model. By the way, the second line is not a valid excuse in this class. Right, so and in practice what tends to happen is that, it certainly is the case that the immediate neighbors will have a higher probability, right? They'll happen more likely, and then how often fence appears next to dog is going to be less probable, or appear less frequently in the data set. But nonetheless, it does happen with some reasonable probability, and we want to capture that in the model. And furthermore, we want to capture it all in a single model, a single embedding that can capture all of these from the relationships, from very peak relationships in the immediate adjacent neighbors to more diffuse relationships where the words are a little bit further apart. And this is one learning objective that allows you to capture all that in a single embedding. Okay. So the original dimensionality of these words are the number of words, right? So we want to learn a low-dimensional embedding, right? So if k equals the number of words squared, that means that we can basically memorize every word pair interaction. It's not very useful. Smaller k assumes that the words lies in some low-dimensional space that can capture all these probabilistic relationships, right? And then it's easier to generalize across words, so a larger k can overfit, in other words. So some interesting things one can do with word2vec. So that's the approach called word2vec. It turns out that if you train on a large enough corpus under this skipgram model with inner product semantics in terms of similarity, you get stuff that looks like this, right? So here we're using V, which is the exit representation, right? The exit of the word representation. So, if you take the embedding location of the word check, plus, so you do a vector addition of the embedding location of the word currency, you get Karuna, which was the currency, or perhaps still is, for the Czech Republic, right? And then here's some just other examples that they looked at in the embedding. So if you do Vietnam, the embedding of the word Vietnam, and you did a vector addition to the embedding of the word capital, these are the top 4 words whose embedding is closest to that vector operation. So it's not perfect, but you get some really interesting semantics here. Yes?
Some of those tokens are more than a single word. So how do they decide what becomes a token instead?
They probably use a standard tokenizer. Yeah. If it's the same, if it's like the same object, named entity object, they probably just grouped it. Yeah. Yes?
You are saying that sometimes there are 4 words like Ho Chi Minh City, right? So you are saying they are the closest words to vector.
Yeah, so you take the embedding, I mean, they tokenize this thing, so this is a single entity. This is a single item. Ho Chi Minh City is a single item in the dictionary. So they learn an embedding for that item, for all these items, and the one that's closest to the embedding of Vietnam plus capital, the 2 embeddings added together, vector add. The embedding, the word with the embedding that's closest to that is Hanoi, then Ho Chi Minh City, and so on and so forth.
You're using like a corpus of words instead of like a single.
We're using tokens. So in practice, they learn embeddings over tokens. And a token could be multiple words. I mean, this is just a standard. You could use using standard parsers to get these groups of words that are entities. You could do other things that are kind of interesting. So let's take the embedding of the word France. You do a vector subtraction of the embedding for the word Paris. Then you do a vector addition for the embedding for the word Italy. And the closest embedding point is the embedding for the word Rome. And so these are just a few other examples, right? So if you do France minus Paris plus Italy, you get Rome. You do France minus Paris plus Japan, you get Tokyo. I mean, some of these don't quite make sense, but although this is only showing the closest neighbor, right? Yeah, so the smaller might be, you know, in second or third place in this particular embedding. You can also do a 2D PCA projection, right? So you know you take all the embeddings for various capitals and various countries. You take your embeddings, you do a 2D PCA projection, and then you draw them out in the space. You get something that's like this. Right? So all the directions, all the arrows, all the vector differences between the country and its corresponding capital are roughly parallel, right? Which suggests that this direction is somehow towards the city version of this country. Now, I should point out that there are some risks with using these types of embeddings because they do capture all the biases of the text, right? So the text was generated with certain biases encoded in them. Then these embeddings will also learn those biases. So not shown here is if you did doctor minus man plus woman, you get nurse, right? Because that's just encoded in the text. So this is so as we use these types of data sets, as we learn these models based on data that's generated by humans, and therefore implicitly encodes all the human biases that we have, then the models that we learn are also going to have the same biases. Yes?
Is there any work that's being done to train a model that can somehow recognize bias?
It's a topic of active research in the community. I don't think there's a solution that's agreed upon yet. But if this is something that you're interested in getting a PhD in, now's the time, right? This is sort of a huge boom. There's a huge boom in understanding bias and fairness in machine learning algorithms and data-driven decision making based off data sets that are collected through biased human decision making themselves. So, we could use these embeddings as features, right? So we've learned this embedding over words, and now we can use, these embeddings, right, as features, right? So before, at the very beginning of this class, we said, okay, let's have a feature vector over some documents, and we spent a long time on bag of words, right? And I think you guys all realized that bag of words, at least certainly I hope you did through calculus competition, it's a reasonable representation, but you can easily imagine much better ones, right? And so one thing is to use the embeddings of these words as a feature representation, right? So I'm going to just end with a few slides on some of the issues that come up with training word2vec. Again, the denominator is sort of the thing that kills the computational cost, right? Like you don't really want to sum over all possible words, right? TPP's model. And so one of the things that the people who worked at word2vec looked at was they looked at a hierarchical approach to defining this probabilistic model, right? So suppose we just made a tree. We just put where the item or the ground items, in this case words, are the leaf nodes of this tree, right? Then we can model the transition probability from S prime to S1, right? As the probability of going from, let's see here, of first going from, given that we're at S prime, we go from A to B and then B to S1. So we have to go, we started the root node and we have to go down the left branch and then go to S1, right? So at every point in time, the normalization constants for these models sum over 2 items instead of the number of items in your dictionary. So we have to learn an embedding point for these virtual nodes in this decision tree, right? But if we do this, the benefit that we get is that the normalization constants are much cheaper because the normalization is always over 2 possibilities rather than the number of items in your item set. Some more examples. And yeah, so then the transition probability just looks like this, right? So from one item to the next item is a product of the probability of going down that path, right? Yes?
Would that be on the right-hand side, given S prime?
You're right, that's a typo, given S prime, thank you. Again, train using bringing this up. And the complexity now is down to the log of the number of items. The complexity for any particular term in here is now logarithmic in the number of items in your item set rather than linear, right, for computing the gradient. Okay, just to summarize, I don't know if this is still the state of the art, this hierarchical way of training. It was as of a few years ago. It certainly speeds up the training process by a lot. And we still have the same representation across all words. And all the use cases are unchanged. You can still do vector, you get these interesting semantics from vector addition, vector subtraction. Any questions on that? Okay, just to recap. So, for embeddings, we have some training data, and we care about some property of the training data that can reconstruct parts of the training data. In this case, sequences of the training data, sequences of ground items of the training data. And the goal then is to learn a low-dimensional representation of the ground items, where the some geometry of the embedding, right, captures a property of interest. In this case, it's either a geometry specified by distance, that's the property we care about, or by the inner product, right? In order to reconstruct these sequences that we've been given, right? In order to do that as well as possible. And the reconstruction of the sequences is measured by the negative log likelihood of the probabilities. So, because these two sort of embeddings with either inner products or distance-based have different semantics, right? So they, when you visualize them, the things are laid out, tend to be laid out a little bit differently. This type of clumping, right? This type of really heavy clumping tends to happen more when you learn distance-based embeddings. Okay, so that's it for this lecture. In the next lectures, we'll look at recent applications, and the next week we'll move on to probabilistic models.